Circuit analysis. This is an overview of some of the main concepts in electrical circuit analysis. We'll discuss branch current analysis and Kirchhoff's rules. Kirchhoff's rules include KCL, Kirchhoff's current law, also called the junction rule, and KVL, Kirchhoff's voltage law, also called the loop rule. And we'll discuss how many equations would we need to solve the circuit. We'll then move on to nodal analysis, loop analysis, and finally we'll discuss some equivalent circuits. So first we have to understand how many nodes and branches we're dealing with. Now the branches are the actual electrical components wired together. So with 4 resistors and 2 power supplies, 1 a voltage source and 1 a current source, that's 6. So there's 6 branches. We have 4 junctions or nodes. To be a little more precise, a node actually is all of the hookup wire, as much of that as you could imagine without crossing through a branch. So this node indicated by the red circle actually is all of this wire. And this is our second node, a third, and a fourth. So we have 6 branches and 4 nodes. Of the 4 nodes, notice that 3 of them are shaded in red and the other one is not. I like to do that because if a node circle is not shaded in, the node joins together exactly 2 branches. So the 18-volt supply and the 24-ohm resistor, that's 2, right, join together at this junction. The other nodes join together more than 2, so I would shade those in. Actually, nodes that join together more than 2 branches are also called essential nodes. And then we'll give the nodes labels. And we'll understand that when we solve a circuit, we're actually completing a branch table and a node table. The branch table shows the volts and amps for each component in the circuit, and I've separated the resistors in the top portion and power supplies in the bottom portion, right? Because the resistors also have resistance. And with volts and amps, we can multiply and get watts, the power, and we should be able to see that the total power supplied by power sources equals the total power delivered to the resistors. There's also a node table and node voltages. Relative to a ground, and GND just means ground, one of the nodes will be called ground, and that means the volts counts as 0 volts at that point. And from that point, walking through branches to other points or junctions, we would get node voltages. I also have this analysis worksheet useful to compare branch current analysis to nodal analysis and loop analysis. Essentially, we would complete the left side here. We have 4 nodes, 1 unshaded, 3 essential shaded in red. 1 is called ground, and we do have 1 known 18-volt constant voltage source. We move over the appropriate cells, and we see that for branch current analysis, we have the number of shaded nodes minus 1 is 2, and that would be 2 junction rule equations to write. For nodal analysis, we take the total number of nodes, subtract ground, and any known voltages where we have the 1. So we also have 2 junction rules to write for nodal analysis, but nodal analysis does not require any loop rules. So that would just be a total of 2 equations. And then for the branches, we have 6 branches. Now we're going to discuss tree branches and chords, but for now, we'll just say that in a planar network, which is a network that can be drawn in a plane, the number of smallest possible loops, also called mesh loops, equals the number of chords. And later on, we'll see what I mean by a chord. So there are 3 loops or chords, and then the other 3 form a spanning tree that we'll discuss later. And we do have a known current, so we'll include that in the table. Then we'll bring over the appropriate cells, and for branch current analysis, It's just the number of loops that we need, and that's how many loop rule equations we write. So then we have a total of 2 plus 3 is 5 equations for branch current analysis. For nodal analysis, we said there are no loop rule equations to write, so we have 2 equations to write. For loop analysis, we take the number of loops minus the known currents, and that leaves us with 2 loop rules to write, and so a total of 2 equations. We start with branch current analysis. So here's the circuit, and here are the solution tables, and let's look at the procedure. But first, we'll remember from the analysis worksheet that we're expecting to write 5 Kirchhoff rule equations, 2 of the junction rule type, and 3 of the loop rule type. So the procedure is to first assign branch currents. We assign a flow in every branch. And you actually do not need to know the direction of flow to get started. You just simply have to put arrows in. However, for our power supplies, we do expect that, for example, the 18-volt constant voltage source would push out currents from the plus through the circuit and back. And also the 1.6 amp constant current source, we expect the positive side to be where the current comes out, which is the opposite behavior to the resistors. If we assume the flow, for example, in the 24 ohms is to the right, then the Ohm's law of volts, V equals IR, is a voltage drop. So the volts goes plus to minus. We decrease in volts going with the flow, whereas we expect for power supplies the volts to increase as we go with the flow. Now, the shaded and unshaded nodes comes in handy now because the unshaded nodes show series connections. So my branch current variable I1, which is the current in the 24 ohms from left to right, must also be the current in the 18 volts coming up to go through the 24, right? Because current is the same in series. For the other 3 resistors, we just make a best guess, and you don't have to overthink it. And so we have our branch currents, and notice that for the constant current source, we actually do not know the volts across the junctions A and B, but we do know the current. So now we write our equations, right? We have 2 junction rules, and the junction rule is an equation for current. Basically, that current entering a junction must leave. So you could see that the current in the 24 ohms, we called it I1, enters junction A, 1.6 amps enters junction A, and out goes the currents through the 10 and 5 ohms, which is I2 and I3. So I1 and 1.6 amps enters, I2 and I3 leave. Now, there's 2 of these equations, which it's basically for branch current analysis, the number of shaded in nodes or essential nodes minus 1. So my second equation now could be B or G. I can take any 2 of the 3 shaded nodes. So I've taken A, I'm going to take B. So at B we have 1.6 leaving, so that's here, and entering comes the currents through the 5 and the 15 ohms. That's I3 and I4. So that's our 2 junction rules. Next, the loop rules. And in the beginning, it's easier just to deal with mesh loops. And so I have 3 small clockwise loops, X, Y, and Z. And the loop rule is an equation for volts. Basically, the sum of the voltage changes around any closed loop must equal 0. So if I start in the lower left and come up minus to plus through the 18 volts, that's plus 18 volts. Then plus to minus for the 24, that's a voltage drop, minus 24 times its current, I1, Ohm's law. And then down through the 10 ohms, plus to minus, that's minus 10 times its current, I2. So that's our loop X. Loop Y, we have our VAB minus, plus to minus, the volts for the 5 ohms. 5 times I3 equals 0. And for loop Z, starting in the lower right, we can go around clockwise. Minus to plus is plus 15 times the current in the 15 ohms was I4, 15 I4. Then up through the 10 ohms, minus to plus. So that's plus 10 times I2. And then minus VAB equals 0. And now we solve the equations. We have 5 equations and 5 unknowns. So let's use Excel to solve these equations. So here's some columns where I will collect together on the left side of the equation the variable terms, and on RHS is the right-hand side for any constant terms. And I just need to record the coefficient of the variables. So for I1, we have 1. I2 and 3 will be subtracted over to the left. So that's minus 1 I2, minus 1 I3. Nothing for I4, nothing for VAB in the first equation for junction A. And the right-hand side, move the 1.6 to the right, and that would be minus 1.6. The second equation, right, we only have I3 and I4 variables on the left. So nothing for I1 and 2. We have 1 I3, 1 I4, nothing for VAB, 1.6 on the right-hand side. Now, next, loop X. If I sort of move these terms to the other side and flip it so this becomes the left, I have 24 I1, 10 I2, nothing for I3, 4, and VAB, and my right-hand side then is the 18 volts. Equation Y, I have nothing for I1 and 2. I have minus 5 I3, nothing for I4, and I have 1 VAB. No right-hand side. The last equation, no right-hand side, and we have nothing for I1, but I2 is 10 I2. Nothing for I3. We have 15 I4 and minus 1 VAB. So now what we would do is compute the inverse of the matrix of coefficients of our variables and multiply by the right-hand side. So let's set up a region 5 rows by 5 columns, and we'll use the matrix inverse function in Excel, equals M inverse of this array. Now, array functions in Excel, instead of just hitting enter, you actually have to hit Control-Shift-Enter. And you know you have an array function when every cell shows the same formula, and the formula has curly braces around it that you didn't put there, right? If I click in here, those curly braces disappear, right? So they are there as a result of the Control-Shift-Enter. Now, to get our solutions, and there's 5 variables, let me just get these headings. Here, I'll actually use the transpose function, which turns rows to columns, equals transpose of this row without the right-hand side, Control-Shift-Enter. All that did was copy my variable labels as a column. And I'll put the solutions here. So now I will multiply, and in Excel it's matrix multiply, that's M mult. And we want this inverse matrix, comma, which in the M mult function means multiply by, and the right-hand side. Control-Shift-Enter, and here's our solutions. Right, so now those solutions go in for the branch currents, and we had that VAB for the current source. And you see that we can now compute volts for the resistances with Ohm's law, IR. So if I multiply current times resistance, I get the volts. If I multiply volts times amps, I get the power delivered to each resistor. If I sum them up, I get the total power delivered, and 21 watts. And I can compare that by taking, for the sources, 18 volts times half an amp is 9 watts, and 7.5 times 1.6 is 12 watts. Add those up, 21 watts. So our power supplied equals our power delivered. The other aspect of the solution is the node table. Now, I arbitrarily said let's count node B as 0, ground, right? You can take any of the 4 junctions and call them ground. If I ground junction B, meaning it's 0 volts, then we can find volts at the other nodes by walking a path through the solved branches, right? If I go from B to A through the 5 ohms, that's minus to plus, that's an increase of the volts for the 5 ohms, that's 7.5 volts. So the node voltage at junction A is 7.5. If I keep going now from A to C through the 24, that's minus to plus, right? I would be increasing from A to C by the volts for the 24, which was 12 volts. So 12 volts plus 7.5 volts is 19.5 volts at junction C. And now if I just come down to junction G, I have 19.5 volts plus to minus 18 volts. That's 1.5 volts. Any of the 4 nodes could be ground, and the others can be computed by following any pathway through the branches, since volts is path independent, any pathway to go from one node to another starting from ground. We now have a complete solution. Next, nodal analysis. Again, our circuit, our solution tables. And we remind ourselves from the analysis worksheet that we actually only need 2 equations of the junction rule variety. Let's look at the procedure. So first we assign node voltages, right? We have our 4 nodes A, B, C, and G. And we assign volts with variables. Now, we also will start by grounding a node, and here I'm going to ground node G, right? We can ground any of the 4. I'm going to choose to ground G, which means by definition it has 0 volts. What that does for us is going from G to C, minus to plus, through the 18 volts, that makes C 18 volts. So we actually only have 2 variables, the volts at junction A and the volts at junction B. And now we write our junction rule equations. And earlier when we looked at branch current analysis, we talked about the junction rule as a rule for currents. And sure enough, this is a rule for currents. Every term is a current. But in the branch current analysis, we had current entering leaves. It's actually simpler to assume that all currents either enter or leave. I'm going to say leave a junction, and formulate the terms as if the current was leaving. Let me show you what I mean. Let's look at junction A a little closer. And let's imagine what would it take for current to leave junction A through the 4 possible pathways. Well, what we would have is, if we assume the volts at A, for example, the current in the 24 ohms, if the volts at A is greater than 18, then VA minus 18 over the 24 ohms, volts over ohms is amps, that would be the current leaving junction A. Of course, if VA is less than 18, then this would be a negative term, so the current is actually entering. The point is not to overanalyze how to decide if current enters or leaves a node. Write the term as if it was leaving, and the math takes care of itself. The term will be negative if the current is actually entering. So, if I want to have all these terms equal to 0, as a current leaving for the terms of the 1.6 amps, it would be negative 1.6 amps leaving and that's this negative 1.6 here, or the 1.6 entering on the right-hand side. I'm just choosing to have a bunch of terms equal 0. So you could see, for example, VA minus 0 over 10 ohms would be this term. And then for the 5 ohms, we'd have VA minus VB over 5 ohms. And this way we don't have to overthink which way's the current going. We just assume it's leaving, write the term, and the term will end up being negative if it was entering. Now for junction B, you can also work this one out as well, right? VB minus VA over 5 would be leaving, 1.6 would be leaving, and VB minus 0 over 15 would be leaving. So here's our two equations. And if I collect like terms on one side and constant terms on the other side, I'm not going to do the Excel solution again. You can do that or some other algebra or solver. But we would get these node voltages, which then go into the node table, right? So nodal analysis, we solve the node table first. Once we have node voltages, we can find volts differences for each branch, right? For example, the 24 ohms connects to nodes C and A. And C is 18 volts, A is 6 volts, the difference is 12. In the branch table, we do not carry a sign, right? You wouldn't say 6 minus 18 is negative 12. We want the absolute value of the difference in node voltages for the nodes that connect the branch to the network, right? So for the 15 ohms, for example, GB, G was 0 by choice, B was negative 1.5 volts. So we say for the 15 ohms, 1.5 volts, not negative 1.5. So even though we're not keeping a sign, in case you subtracted an order that gets a minus sign, what we do get is the direction of current, right? Let's go back to the 24 ohms. Since junction C is 18 volts and junction A is 6 volts, 18 is greater than 6, current in a resistor flows from high to low volts. So we also get the directions of the currents at this point. Last but not least, we can then use Ohm's law to get currents by taking volts over ohms and getting amps. And in the case of the 18 volt supply, since that was in series with the 24 as indicated by the unshaded node, we were able to copy the half an amp that we got for the 24 ohms. We have a complete solution. And again, our watts calculations matches what we had earlier. Now, sometimes with a different choice of ground or other issues in a circuit, a more complex circuit, there is a construct known as a supernode that sometimes occurs. And I can make the supernode idea occur if we ground, say, junction B. Right? If we ground junction B, then we have an unknown volts at A, VA, and we also do not know the volts at C and G. But the volts at C and the volts at G are related by the known voltage source. So I actually still only need two unknowns. I could say VC is my second unknown, and that would make VC minus 18 the volts at G. Or I could have said VG and then VG plus 18 at C. So a supernode is the union of the known voltage source and its nodes, right? So this whole blob is a supernode CG. So our second equation, if we focus on supernode CG, you could see we have 1, 2, 3 pathways for current to enter or leave supernode CG. So the first term happens up at C, right? So again, same as with earlier, we take the volts where we are working, CG, so C, volts at C minus volts at A, right? So VC minus VA over 24. That's the current leaving the supernode. Now, down here at junction G, we have VC minus 18 minus VA, right? We start with where we are. VC minus 18 minus VA over 10 is this middle term, and that's expressed to be a current leaving. Of course, like we said earlier, if that will turn out to be negative, which means the current's actually entering. And last but not least, VC minus 18 minus 0 over 15 represents the current leaving the supernode through the 15 ohms. Now, collecting like terms and constants on the right and doing the algebra that I'm not going to show, we get these node voltages that are different from before when we had node G grounded. Plug those into the node table and convince yourself that differences in node voltages produce the same branch voltages, and therefore the branch table is unchanged. All that changed was the node voltages because we chose a different node to be grounded. So I'll go back to grounding G, and it turns out with just a single voltage source, if you ground either node C or G, you avoid the supernode construct. But if you ground another node, or there are circuits where you have multiple voltage sources or independent or dependent sources, you sometimes cannot avoid the supernode. In any case, here's our solution. Next is loop analysis based on mesh currents. And we start with our circuit and the solution tables. And we remind ourselves that we're expecting two equations of the loop rule type. And here's the procedure. So we actually start the same way as branch current analysis. We assign flows through each branch, right? Branch currents. And here's my branch current variable, same as before when we did the branch current analysis. Now, for branch current analysis, we also use these mesh loops, the smallest possible loops. Like think of a screen door, right? The small little holes, like little mesh loops. But in mesh analysis, we treat each loop as a mesh current, Ix, Iy, Iz. And the idea now is to express these branch currents, I1 through I4, in terms of mesh currents. But we first have to understand a construct known as a supermesh. Now, a supermesh occurs when a known current is shared by two meshes. So what's a supermesh? Well, it's a union of meshes and shared known currents, right? So mesh Z and mesh Y shared a branch with a known current. The union of those meshes and that branch is a supermesh. And you can see the way I've shown the mesh current as clockwise, if IZ was what we called the current in mesh Z, by the time it reaches the top, it is joined by the 1.6. So mesh current IY is 1.6 plus IZ. The point is we get an equation that keeps the number of unknowns to 2. And whether or not you want to count Iy as the variable, and in that case you would have Iy coming in, and Iz would be Iy minus 1.6, or what I'm doing is I have Iz joining the 1.6 plus to get Iy. And now we're ready to write the branch currents in terms of the mesh currents, now that we have our supermesh understood. The current in the 24 ohms, I1, and also the 18 volts, is only affected by mesh X, so I1 is Ix. For the 10 ohms, the branch current is shown going down, Ix is down, Iz is going up, so Ix minus Iz is I2. The 5 ohms is just the 1.6 plus Iz. And then last but not least, the current in the 15 ohms, the branch current that we labeled, is going to the right, but we have IZ going to the left, so I4 is minus IZ. So now we're ready to write our loop rule equations. And we have two, right? We have mesh X and super mesh YZ. Remember, the loop rule is an equation for volts. We're looking for the sum of the voltage changes around a closed loop equals 0. And that is why the branch current setup is so important. The pluses and minuses on the resistances are key to getting these terms correct. If I start on the lower left and go clockwise around mesh X, I go minus to plus, so plus 18 volts. Plus to minus, so minus the Ohm's law volts drop, 24 ohms times I1. But I1 was IX. Now, down again, plus to minus, that's a decrease, minus 10 ohms times the current I2, which is IX minus IZ. Now we're back where we started, so that's our loop rule for mesh X. For super mesh YZ, we have a little larger loop. Let me start in the lower right corner, and I'll go clockwise. So minus to plus is plus 15 times I4. I4 was minus IZ. Now minus to plus, so that's plus 10 ohms times I2, which was IX minus IZ. And last but not least, plus to minus, so minus 5 ohms times the current I3, which is 1.6 plus IZ. So these are the two equations that we can solve for mesh currents. If we collect like terms on one side, constants on the other, and do the algebra, we get our mesh currents. If we plug into our branch currents, we now get our branch currents because they were known in terms of mesh currents. Now that we have the branch currents, we go ahead and put those in the table. And then with all of the currents through the resistors, we use Ohm's law to get the branch voltages, and then we compute our power and get our total power by summing up all the power. Now, we can also, once we know most of the voltages in the branch table, we can complete our node table. Again, we have to arbitrarily ground a node. Since I earlier grounded B and in another example grounded G, I thought, let me try A, right? So I'll ground junction A, which means by definition it has 0 volts. Then we can travel to any other node through a known branch to get the node voltage at the other node. For example, if I go through the 24 ohms from A to C, minus to plus, I've increased by the volts for the 24 ohms, 12, right? So the node voltage at C is 12. If I just go straight down to G from A, plus to minus, I've decreased by 6. So negative 6 volts is the node voltage at G. Then if I come through the 5 ohms plus to minus from A to B, I've decreased by 7.5 volts. So the node voltage at junction B is negative 7.5 volts. That then lets me also get the branch voltage for the 1.6 amps, right? It was the difference between A and B, which is the difference between 0 and negative 7.5. In absolute value, that's 7.5. We also can get the 7.5 because the 1.6 amps is in parallel with the 5 ohms. And in parallel, voltage is the same. So we could have just copied the 7.5 for the 5 ohms down here as well. That's our complete solution. Next is another type of loop analysis based on chord currents. We have our circuit, our solution tables, and again, we are expecting 2 loop rule equations to write. And similar to the mesh analysis and the branch current analysis, we start by assigning branch currents And so we have our flow arrows, same as before, and our branch current variable, same as before. At this point, we need to separate our 6 branches into tree branches and chords. So we're interested in the idea of a spanning tree, and let's have a look at what that means. I've shown a copy of the circuit, but without all the details, just showing simple lines for each of the 6 branches. And I'm going to show a number of possibilities for spanning trees. Now, in each of these 8 cases, I specifically did not want the 1.6 amps to be part of the tree because that's a known current. It turns out that once we have a spanning tree, the remaining branches are called chords. And a spanning tree is such that it's a set of branches such that from any junction you can get to any other junction through tree branches only. And notice that for the trees, there are no closed loops. And again, the remaining branches then are chords, and you can see we have 3 chords and 3 tree branches, and it is the chord currents that uniquely determine all of the branch currents and the loops that we will be using. Let's take an example with this as our tree and chords. Now, how do we construct the loops? Every loop is constructed with a chord and then only tree branches. So you can see for every chord, there's only one possible loop that allows us to have that chord and only tree branches. So these are the loops that we will use. And the reason for ensuring that the 1.6 amp current source was a chord was that one of the loops is known, right? So there is no super mesh construct needed in chord current analysis. And I'm showing loop Z as counterclockwise. It actually doesn't matter if you show it clockwise or counterclockwise. So I'm showing our loop X clockwise, our loop Z counterclockwise, our loop Y, which is known. 1.6 amps is the loop that includes this chord, the 1.6 amp current source. That's a known loop. In any case, we want to express the branch currents in terms of these loop currents. So again, I1 is Ix, same as we've seen earlier. However, I2, the current in the 10 ohms, because I have a different direction for Z, it's Ix plus Iz. Both Ix and Iz go down through the 10 ohms. So Ix plus Iz. I3 for the 5 ohms goes to the right in our branch current setup, and that's minus Iz plus 1.6. So 1.6 minus Iz is I3, and I4 for the 15 ohms, that just matches the direction Iz, so Iz. And now we write our loop rules for X and Z, loops X and loop Z. And notice that I show loop Z as counterclockwise, and that had an effect on how the branch currents relate to the loop currents. But it actually doesn't matter if you go clockwise or counterclockwise for the loop rule to get the voltage term. So I'm just going to go clockwise for both loops. So again, for the lower left, up through the 18 plus 18 volts, minus 24I1, which is Ix, minus 10I2, where I2 is Ix plus Iz, equals 0. That's our loop X. For loop Z, if we start at G and go up through the 10, that's plus, minus to plus, plus 10 times I2, which was the Ix plus Iz, plus to minus. We go by the signs of the branch currents, plus to minus, so minus 5 times I3, which is 1.6 minus Iz, and then here minus to plus through the 15 ohms is a plus 15 times I4, which was IZ. So we can, do the algebra, which I'm not going to show, and solve for the loop currents and plug those in to get the branch currents. So it's sort of a similar procedure, but there's no supermesh needed. We just have to take care that the known current sources are chords, not part of trees. We put in the known currents. We calculate volts with Ohm's law. Same as before, we've seen this a few times. We get our node table by grounding any junction. Here I'm grounding C, and that would give me minus 18 volts at G, and you can convince yourself from the branch table that the node voltages at A and B are these values. As another example of the loops generated by chords, let's choose a different tree. Let's try this one. Again, for each chord, you form a loop with the chord and then only tree branches. So we would have this outer loop, this loop here, and this small loop. Right, so our loops X, Z, and the 1.6 was known would be these three loops, and this would be the branch currents in terms of loop currents. We have very similar equations as before, but you can convince yourself that these would be the terms following loop X and loop Z. And we would get these loop currents and then these branch currents, and from there the table would produce itself as before. Now, so far in the various methods we used, we generated the same branch table, and I'm just showing every possible node table depending on which node was grounded. And that's loop analysis. Is mesh analysis a subset of loop analysis? Well, here's an example network, 3 nodes, 6 branches, and it turns out that only 2 of the 6 branches are necessary to form a spanning tree. Now, if we wanted to have mesh currents come from chord currents so that mesh analysis, yes, is a subset of loop analysis, we would have to have this branch be a chord so that this inner mesh loop uses that chord current and the 2 tree branches. Now, that makes the outer 3 branches chords. And you can see that, yes, we can get this mesh loop and this mesh loop with the chord and a branch from a tree, right? Chord and tree branch. But this last chord, in order to use tree branches, it's not a mesh loop. No matter how you look at this is the simplest network I could come up with that demonstrates that mesh loops are not necessarily derivable from chord currents. So mesh analysis is not necessarily a subset of loop analysis. Next, let's look at some equivalent circuits. Here's our original circuit and the solution tables. And I'm just making a copy of the circuit. I actually switched the 1.6 amps with the 5 ohms, but that doesn't matter because these 2 branches connect between junctions A and B. And first we'll look at the transformation of sources. The transformation of sources lets us replace a constant voltage source in series with a resistor with a current source in parallel with the same resistor. Or a current source in parallel with a resistor can be replaced with a voltage source in series with that same resistor. So when we do that, the 18 volts in series with 24 ohms became a current source in parallel with the 24 ohms. And the way this works is you would get the current in the current source as the 18 volts divided by the 24 ohms. Now, the 5 ohms and the 1.6 amps that were in parallel are replaced with then a voltage source in series with the 5 ohms, and the volts is found by the product of the 1.6 amps and the 5 ohms, so 8 volts. Now, another possibility is series resistances. Whenever you see resistors in series, you can combine them into a single resistance and add them, right? So 5 and 15 is 20. Now I'm going to transform sources again, just the voltage source in series with the 20 ohms. I'll make a current source, which will be 8 divided by 20, or 0.4 amps, in parallel with the 20 ohms. And now we have 3 resistors in parallel, and I can combine those as the inverse of sum of inverses, right? So 1 over 24 plus 1 over 10 plus 1 over 20, and take 1 over that result. I also have 2 current sources going from G to A. I'll just add those as a single current source. So adding my current sources from G to A and getting the equivalent parallel resistance, I get 5.217 ohms. And at this point, I can see I have a single current loop, and the current goes from A to G through the resistance, so the volts goes down, and that volts would be the product of the 1.15 amps and the 5.217 ohms, and that's 6 volts. So node A is 6 volts higher than node G. So if we bring in the solution table and I say node G is ground arbitrarily, I then have my node A is 6 volts, as we just found. I also, with G grounded, know that node C is 18 volts, right? Going from G to C, minus to plus, 18 volts at C. And I then can get some of these branches based on what I know so far. Now, so far, I redrew the circuit a little bit, and I did transformation of sources, added series resistances, did transformation of sources again, and then parallel resistances, and I combined my current sources. I actually want to go back now to this shaded circuit. After all, equivalent circuits is an iterative process where you replace a portion of a circuit with an equivalent circuit, hoping to get some information towards your solution. So now I'm going back to the shaded circuit, and we already figured out that between A and G is 6 volts. So I can replace everything that connects to nodes A and G that I've highlighted with 6 volts. And that's just as good, that's equivalent for the remaining items in the circuit here. So then you can see I have a single loop. 8 volts is higher than 6. And they're competing with each other. The 8 volts is a larger volt, so the current will be counterclockwise. 8 minus 6 volts divided by the series 15 plus 5 ohms is 0.1 amps. And in this equivalent circuit, the only resistance that was original is the 15 ohms. And so we know it's 0.1 amps going from G to B through the 15 ohms. So I can then put that in. I have 0.1 amps for the 15 ohms, that's 1.5 volts. And going from G to B, I'm going down in volts. So if G was grounded, that makes B negative 1.5. I now have the node table complete, so I can get any branch voltages as volts differences that I don't have so far, and Ohm's law to get missing currents. And that's our solution, and this was the pathway through equivalent circuits that we took. So as a procedure, equivalent circuits, it really isn't a procedure, right? You look, you may see something that could be replaced with an equivalent circuit, you try it. hopefully looking to get some sort of a solution. Sometimes with experience with various types of equivalent circuits, especially series and parallel combinations, you can very quickly get a result. But other times, you're better off going to branch current analysis, nodal analysis, or loop analysis. Now, a little more on equivalent circuits. I'll go back to the original circuit and the solution table. A very powerful equivalent circuit, when you're looking for just one piece of information, is the Thevenin equivalent circuit. And I have a separate video on this, but just to see this example, suppose I wanted the current in the 15 ohms. We saw earlier with the pathway we took, there was a fair number of steps. So I want the current in the 15 ohms. With the Thevenin's equivalent circuit concept, we would treat the 15 ohms as an output across junctions B and G, and that output is not shown. And the rest of the circuit is shown, and the Thevenin theorem is that the rest of the circuit, missing the output, can be replaced by a Thevenin volts in series with a Thevenin ohms. And to get the Thevenin volts, we basically just consider what's going on with the circuit without the output, an open circuit output. And we see that in this particular case, we have two loops that are joined only at one node. There's not a return. So in other words, no current can flow from one loop to the other because there's no pathway back. So these are separate loops. And so the Thevenin volts from G to B, we can say, well, it's the volts increase across the 10 ohms minus the volts decrease across the 5 ohms. Now for the 10 ohms, that's a series circuit, the 24 and the 10 in series connected to 18 volts, and that's also called a voltage divider. So the volts for the 10 ohms is the 10 itself over the sum of the two in series, 10 and 24, that fraction of 18. Now for the 5, we saw we were subtracting that. That's just the Ohm's law, 1.6 amps times 5 ohms, or 8 volts. And so we get our Thevenin volts of minus 2.706 volts. Now for the Thevenin ohms, we short circuit any voltage sources and open circuit any current sources. And then we can see that we basically have the 24 and the 10 are now in parallel, and that result in series with 5. So 24 parallel 10, that result added to 5, that is 12.06. So we bring in the Thevenin equivalent circuit and this time connect the output, and we see that we have a single counterclockwise loop. We have 15 plus 12.06 in series, that's 27.06 ohms, and so the current is 2.706 volts divided by 27.06 ohms, that's 0.1 amps. So we found the current in the 15 ohms very quickly with just one equivalent circuit. We put that in the table, and we can continue, and one way to go here is to just focus on junction B. With the junction rule, we realize that we have 0.1 amps coming up to B from G through the 15 ohms. 1.6 amps is leaving to A, and that must mean then that the difference, 1.5 amps, must be coming down to B through the 5 ohms. So with the 1.5 amps in for the 5 ohms, that gives me 7.5 volts, and I can end up completing some of the node table as we discussed earlier, and we're actually able to complete the entire table just from those steps. So without going into every step, I have a separate video on the Thevenin's equivalent circuit. We identified the 15 ohms as an output, produced the Thevenin circuit with the output, and then did a junction rule at B, and just by Ohm's law and some analysis, we were able to complete the rest of the solution tables. And there we have it, an overview of circuit analysis.